Welcome to section 3.5, the pre-class video assignment. So here we're going to look at solving initial value problems using the Laplace transform. So there's a couple of properties here we need about what the transform of a derivative looks like. And once we have those in our pocket, we can use them to solve initial value problems in kind of a slick way. That is, we basically solve the whole problem all at once. We don't need to solve a DE and then apply initial conditions. The Laplace transform would basically solve the whole initial value problem all at once. So the first thing we need is, what is the Laplace transform of the derivative of a function? The Laplace transform of f prime. So this is actually the theory. This is the result. The Laplace transform of f prime is s, the independent variable s, times the Laplace transform of f minus f of 0, which is, of course, our initial condition. Again, this can be abbreviated. We generally have where Laplace transform of f of t is, again, we've been calling this big F of s. And in this case, it's even convenient to just drop off, forget the this f of s is confusing. This is function notation. This is not a product of f times s. And if this can get confusing, so it is actually practical to just drop off the sort of suppress function notation and write this in without it for now, so that this is really just s f minus f of 0. Again, so this is actually the result. So let's take a look at why that is. There's kind of a nice little proof here, fairly easy to follow, I think. But again, if we want to know what the Laplace transform of f prime is, we can just apply the definition of a Laplace transform. That is, we do the improper integral from 0 to infinity, f prime of t e to the minus st dt. And then the clever bit here is, I don't know what f prime of t is, so I can't directly apply the Laplace transform, but maybe I can actually integrate this by parts, because for example, if I pick my parts, if I pick u to be e to the minus st, which is a bit non-traditional for by parts, but then I pick dv to be f prime, this works because, of course, we can integrate f prime. We know the antiderivative of f prime is f, and I can differentiate e to the minus st. I would get minus s e to the minus st. So by parts says we get uv, so e to the minus st f of t from 0 to infinity, plus the integral of v du. So v du is the product of these two. So there is a minus minus plus s e to the minus st f of t dt. So if we look at this guy here, this is an integral with respect to t, so s can come outside. S is a constant with respect to this integral, so I can bring the s outside. And then if I look what I have here, this is just the definition of the Laplace transform of f. So we end up with, okay, well, so we can put b in here, put 0 in here. We get e to the minus sb times f of b. And again, as long as f is a function that has a Laplace transform, this limit will go to 0. So we will still have this minus f of 0 present. And then we have s times what is effectively the Laplace transform of little f, which is big F. That is what this says. And again, it is actually more convenient when we work with these things. It's going to be more convenient to drop off the function notation here for big F and just call it s times f minus f of 0. So this is a biggie for us for this section. We will see this lots of times. So we want to know this rule, I guess. We want to commit that rule to memory. All right, so otherwise, that tells us how to take the Laplace transform of a derivative. And if you think about it later on when we've gotten through this stuff, what you'll perhaps hopefully appreciate is that this is what makes this whole thing work. Taking the Laplace transform of a derivative can be represented in terms of f of s, the Laplace transform of the antiderivative of the original function. It is not in terms of derivatives anymore. So taking the Laplace transform of a differential equation will no longer be a differential equation. It will be an equation in terms of f. So that is what makes this method work, basically. This helps us for first order differential equations because it tells us how to do the derivative of a first order tells us how to do the Laplace transform of a first order derivative. We, of course, will need some higher order ones as well. We will probably just be sticking with no higher than second order, but we will need to figure out Laplace transforms, a rule for taking the Laplace transform of higher derivatives. So there is a general theorem stated here. I don't think we will need anything other than second order. So I can prove this in terms of second order. So in order to prove the second order case for this formula, we have the following. That is, we can go ahead and assume the first order derivative as we just proved it. So then you do the Laplace transform of f double prime, and keep in mind that we're really looking at this as being the first derivative of f prime, and then we can apply this rule. So this is the Laplace transform of the derivative of f prime. So that is s times the Laplace transform of f prime minus f prime of 0. This is just by the rule we just proved above. So applying the rule above to f prime instead of f. And then all I have to do is, that rule also tells us what this is. So I can put back what this is. And this is what the original rule told us, and clean it up. Distribute the s, we get s squared f of s minus s f0 minus f prime of 0. And again, this is your Laplace transform of a second derivative. So these two things are extremely important for the rest of our semester. Actually, we will see these two things as our way to work with Laplace transforms and differential equations. Again, this rule there is sort of a pattern here you can recognize when I try and remember this. It's notice that the power of s, case n equals 2, we start with an s squared, and then it goes down to an s, and then a 1. So it's kind of going s squared, s to the 1, s to the 0. And then these are sort of going in the opposite direction. A Laplace transform is kind of an integral, and then that would be kind of a derivative, and that would be kind of another derivative. And again, these are evaluated at 0. So the pattern is imperfect, but you can kind of, I can kind of make sense of it and remember it this way. All right, so that is basically the nuts and bolts of what we need to do problems in this section. So here's a little bit of practice using those rules. So again, make a note of these rules, this guy and this guy, and again, this is these Laplace transforms. So make a note of those and give them a go here. So here's a few examples. What is the Laplace transform of y double prime minus 3y? So again, first of all, linearity. I can do this term by term. So the Laplace transform of y double prime minus 3 Laplace transform of y. So this is a second derivative. So the Laplace transform is, again, I'm going to call it s squared, and then the Laplace transform of y is big Y. Again, I will suppress function notation, and then we would have an sy0 and a minus y prime of 0. So all of this is this guy, right? This guy becomes this by that previous rule. And then we just have the Laplace transform of minus 3. Laplace transform of y is minus 3y. So this would be it. This would be our expression. We could clean it up and maybe combine like terms. There is, again, big Y's and so on, but that's basically it. Again, here is another example. This is the Laplace transform of y double prime. Again, we see this is that rule. Then we have 4 times the Laplace transform of y prime. So I have 4 times, this was the first rule. And then you can apply your initial values and clean it up a little bit. Again, you could combine some like terms here, but essentially this is how this works. So again, this is usually how all of these problems will start, is by applying a Laplace transform to the left-hand side of a differential equation like this. Here's another one. Again, you can pause the video if you want to stop and try them. But here, give this a go. Here's a question with a couple of parts to it on my open math to try. Okay, so let's just see in some simple cases how we can do this. So here we will look at using a Laplace transform to solve a first order non-homogeneous DE or non-homogeneous initial value problem. This has to be an initial value problem. We will do some second order together in class. But the idea would be we start off by, here is our DE, we start off by taking the Laplace transform on both sides. Again, you can apply the Laplace transform to both sides. On the left-hand side, we can use these properties we've just learned. The Laplace transform of y prime is s big Y minus y sub 0. The Laplace transform of 4 little y is 4 big Y. So this is our left-hand side here. And then we need to basically go to our Laplace transform table and remember, what is the Laplace transform of e to the minus 4t? This is on your table. I forget the number. I want to say it's like number 11 or something. But again, this is what we get from our Laplace transform table. So appreciate what happened here. This is kind of subtle, but it's kind of awesome as well. We start with a differential equation. We apply Laplace transforms to it. And now we have an equation that is no longer a differential equation. There are no derivatives anymore. The thing we want to find in this equation here is we want to find what big Y is. Big Y is the Laplace transform of the solution function y of t that we seek. So we want to, our next step is we want to solve for big Y. So the way to do this is gather your big Y terms together, factor out the big Y, move everything else to the other side. So put the minus, add 2 to both sides, and then we can solve for big Y by dividing. So this is sort of the first sort of critical first half of a problem like this, is to apply Laplace transforms on both sides, solve for big Y. And at that point, this is a statement of the solution function we're trying to find has this big Y as its Laplace transform. So give a couple of those a go on my open math. Here's the first one. And then there's a second one. All right, so once we have a hang of that, what is left to do is, if we want to go from the Laplace transform of the solution to finding the solution itself, we'd have to do an inverse Laplace transform. I would need to invert this function by Laplace transforms. So again, we learned a little bit about that in a previous section about inverting Laplace transforms. So we would want to, again, work backwards from our Laplace transform table to invert. This particular example is fairly straightforward. This is a number 16 directly, which comes out this way. This is a number 11 with a 2 in front, right? We put the 2 in front, factor out the 2. 2 times 1 over s plus 4. 1 over s plus 4 is a number 11, which comes out like this. So this is, in fact, y of t. This is the solution to the initial value problem. All in one go. There's no plus c's here. This is the particular solution that solves the DE and satisfies the initial condition. So kind of slick way of doing it. So there's a couple of, again, first order examples, kind of like this one for you to try just to get the hang of it. So here's the first one. And then there's a second one to try. Okay, and then before we go, that's where we're going to leave it for the notes. We're going to finish the rest of the notes together in class, but just a little look ahead. This last one was fairly easy to invert. They can be a lot trickier than this to invert. So some examples we will see, like here, we have this issue of, okay, we might need to factor, we might need to do partial fraction decompositions. And again, this one is actually kind of an unpleasant partial fraction decomposition. We'd have to figure out how to do those. I have a couple of just more tricky partial fraction decompositions, kind of as a preview for the sorts of things we will see when we finish this packet together. So here is the first one. And then there's a second partial fraction decomposition to practice on. Okay, well, that will be it then. We will finish this up together in class. Thank you.